Great. Hello, everyone. My name is Slava. I'm from Aurora Labs, and today we talk about how to write a simple game on a BOS using Near and Aurora stack. So first of all, let me introduce myself. I'm working as a DevRel and integrations developer at Aurora. Today we will have like two main heroes. Unfortunately, Michael isn't here, but he is the original author of the project, which I'm presenting today. I'm actually managing the Aurora developer portal. You can visit it at devaurora.dev. And the whole presentation you will see here is actually based on the article written by Michael Bergzar. So my advice, if you want to know more and read the details, please go to devaurora.dev and learn more there. I also wanted to say a few more words about the presentation itself. Like the BOS GG gateway, which is usually used for Ethereum-based, like Aurora-based BOS components, has actually inspired me to use some nostalgic concepts here and to use the design from the really old video game I've been playing at the late 90s on my TV, actually, with Sega station. So it was called Golden Axe. I'm not sure if you have ever heard about that, but I've used like a gameplay from it to present today. So let's continue, and here we can see the planned adventure for today. So we will follow a simple set of rules to create the project, and those are just to push the complex operations to the near blockchain, to use Aurora for easy onboard of our users, and to do the state management there using a Solidity contract, and build a frontend on BOS. So overall architecture will look like that, where like BOS UI will just request something from Aurora contract. Aurora contract will do the cross-contract call with the Near contract. Near contract will respond with a callback, and everything will just cycle, and you'll be able to play your game. Overall, it's kind of the same way you can do that with the regular JavaScript and WASM. Like if you have some complex operation on your front end, you can encode it in WASM, and it will be more efficient. So if you come just from a regular like Web 2 perspective, it looks kind of like that. So let's first start with the Near contract, and Michael could actually represent the whole team for the adventure. So he is the Rust wizard in this context. So let's go into the Near testnet first and catch all of the aspects of the tic-tac-toe game into the contracts net. But first we need to decompose the problem, right? And to learn a little bit of tic-tac-toe theory. That's what Michael actually did. And he pushed some ideas gnomes and got the ideas how to evaluate the moves in the game, how to represent the game state, and how to predict the next move overall. In terms of the code, which is written in Rust for the Near, it's just like we have structs for the cell state. You can see it could be empty, it could be X, it could be 0 or circle. And the game state will be just represented as an array of the cell state. So it will be just like what's called row major representation of the tic-tac-toe board. And for the moves API, the main two things he needed to do is to evaluate the move, how good the move is comparing to the previous board state. And also the main function is called getMove here, which by receiving the game state produces the move result. So that's the main, like the core function of the contract. Now we are ready to actually produce the Near contract, but we need to link everything, and then we will test it using the BOS component on Near. So we have that big core getMove function, And Michael has some weapons, like the near binge macro and some Borscht wrappers to serialize, deserialize inputs, outputs. And that's how, using Rust magic, he just finishes the contract. And now we just jump into the contract details. So two main things here is that we just pattern match get move result, and as you can see, we just can have like two different results, like the next move or game over, when we already can we already know who won the game, and we return the struct called get move response there with winner field and updated state for the board to be displayed on the BOS component. So let's write some basic UI right now. We'll need some HTML, CSS, and JSX and state management there. So Michael just got some representation for the game board, state managed, and used near view function just to pull the near contract and to get result. So this UI will be only for the stateless representation of the tic-tac-toe game with no state preserved. And the core of this BOS component is actually inside the near view function, which calls the tic-tac-toe contract already deployed to near with the get move method name and the board state. Yeah, and UI just includes game board, player selector, like do you want to play for access or nodes, and the new game button. So overall, it will look just like that. And what's interesting is that the feedback when playing the game will be almost instant. I can quickly show it to you. Let me find. Yeah, this is the one. So let me click. You see, I just clicked, and you already have the result. I clicked, and you already have the result. And if I click one more time, so there is no time. You just using the pure view function. You don't need to pay anything, and everything happens instantaneously. Let's continue. But we need to move further, and now we need to write our Aurora contract. Now Michael becomes XCC warrior, cross-contract calls, and it should be an easy mission, right? Like just to write some Solidity wrapper around that, but it won't be so easy if you don't know how to do the cross-contract calls. That's why let's take a look at the next slide, which describes how are we usually working with, like how cross-contract calls from Aurora to near work. So usually, if you have contract on the Aurora Solidity contract, it calls cross-contract call precompile. There's some peculiar details about how, like, it handles synchronicity of the EVM and asynchronicity of the near itself, which you can actually read in the repo called Aurora Contracts SDK. I've included the link below. But we won't go into those details. Overall, after calling that precompile, there will be a call to the contract sub-account, which will have the same name as the, like it will include EVM hash. It's called ABCD here, but it will be like some hashed values there, .aurora on near. And it will be the representative of that contract on near, which will call the target contract on near, and after that, the callback will be executed. Overall, everything which happens here happens using what's called near promises. Yeah, and we will see details on the next slides. So using some XCC karate, Michael produces those promises, the near call promise and callback promise, joins them together, and transacts. That's how he beats that giant. Let's take a look at the details. So what you can see here, the struct called promise create args is actually the struct which creates promises. So the first promise is actually calling the tic-tac-toe near contract with get move method. And the next one called Aurora call will be we'll be calling our contract, our Solidity contract. You can see address this at the first argument there. And we'll call computer turn callback function here with the new data received from the new contract. So, and the last line here, it just composes the promises together and calls transact method to execute everything. Yeah, and the next part is how exactly we unwrap the results. So we have computer turn callback function, which actually called inside the Aurora promise here. It gets the result, unpacks it, and overall it just updates game state here. Game's player is just like a map. We will see it next on the next slides. So while we were discussing DETHCC, Michael has actually managed to finish the Solidity contract, and he's ready to show us the manuscript. Let's take a look. So on this slide, we just see a state and the needed structs for the Solidity contract. Like the first part of the picture includes just structures used by cross-contract calls, like near and vnear and some Aurora SDK primitives like promises. And the main state of the game goes into two maps. One maps for storing the game states for different users. So we have like kind of like a multiplayer game in terms of like storage. And also legal moves, which could be done, and turn event, so you'll be able to index the data on the blockchain. Yeah, and here we have some initialization done. So just inside the constructor, you can see that we are using access roles here. For the message sender, for the author, we assign owner role, and for the callback from Aurora SDK, which is actually implicit account of our current contract, our representative on here, we are assigning the callback role, so it will be able to call callback function of our Solidity contract and only it, with like no other person or contract being able to do so. And we need to do initialization here because we need to create that near counterpart account for our Aurora contract. And to do this, we need to call once the tic-tac-toe contract with getMove function and have some vnear or wnear, wrapped near coins on the contract address. That's why author here, the owner, in this case Michael, transfers some storage deposit to the contract. So the contract will spend it to cover for the near storage for that counterpart. Yeah, and inside game functions of the Solidity contract, they are pretty simple. So we just have like new game, creation of the new game, where you just like computer take turns, and also player turn, well, when like both player and computer take turns, and that's it. So, and take computer turn is a cross contract function which we've been looking at previously with those promises and transact method. So, and the final part, we now need to create the UI representation on BOS.gg. So now Michael is in a role of the UI ranger here. So he comes to the final boss in the game, and he sees that, yeah, boss has some really early adoption here and some limited GSX variant. So he has some struggles because he cannot use async await directly, and he just needs to join promises using then syntaxes and stuff like that. He can use use effect, and testnet of Aurora isn't recognized yet from that gateway, so it just says unrecognized. But still, you can go like you can transact, and everything is working great there. So just by using his HTML, CSS, and React skills, Michael defeats the final boss. And now he's ready to present his UI code for us. What we have here is just like we get in the contract ABI to communicate with the contract from the UI and initialize some state like game board, pending player, etc. We also need to create like a new game. We have the same new game button to start the game, and some state updates for when you like receive new game, new board state from the contract. You need to put it there, so you can see that we just updating the board state here with the result. Yeah, and the heart of the state management here lies in the player turn functions. So when player move, we just call take player turn method on the contract. And after receiving the results from that promise, we just updated the state, and that's it. We also have some really simplish styled cells components, which are just like table cells in HTML. And we have game board, player selector, and new game button designed in the same way it was done on the near boss component. So the final UI looks like that. And we can do a small demo now. Yeah, we have the recording here, which represents the gameplay overall. I just don't want to spend much time. That's why I put the video here and playback speed 2, because we need to do some MetaMask and to wait for some RPC calls, callbacks to come back. So as you can see, it has more delay overall comparing to the stateless BOS component, but nevertheless, it still works. You can play with it and have everything managed. Let me wait. Maybe we will have a winner now. Probably one more call. Let me just fast track a little bit to the last turn. Yeah, so we have a draw here. We have a draw, and we can start a new game. After new game, we just need to do one more transaction, wait some time, and it will be reloaded with the first turn done by the near contract. Oh. Yeah, so that's it. That's it. Let me go back to the slideshow. So in conclusion, what we can say that like the main lesson learned here is that we can efficiently combine Aurora, Near, and BOS together to create in an easily way with no infrastructure deployed, with no servers, a way for the users to interact with the blockchain, and easy onboard users using Aurora, using either Aurora Plus, but really soon we will release Aurora Pass on the next week. We are using like Aurora contracts for the state management in this case. Yeah, I will share the presentation. I hope it will be included to the recording, and you will be able to see the links. But you can just go to the devaurora.dev developer portal right now, or just find me to ask more questions after the presentation, and I will happily answer that. Thank you, everyone, for attention. Any questions? I'm ready to answer. Thank you.